Okay, now that we've introduced the exponential function, we're going to look at some application. And one of the things it's very useful for is in dealing with compound interest. So let's talk about what compound interest is. So first of all, what's interest? This is a charge, right, for borrowing money, usually expressed as a percent, called the interest rate. And you can be borrowing money from a bank, for instance, taking out a loan. You can also be looking at from the standpoint of an investing company or bank borrowing your money, where they pay you interest on an investment. So I mean, you can be at either end of the interest. You can be the one receiving the interest for investing your money, or you could be the one paying the interest if you, for instance, take out a loan. Now, simple interest is a way of calculating interest by just multiplying the amount that you invested, which we call the principal, and we use the letter capital P for the principal. That's the amount that you invest or borrow. And then the interest rate, which we'll use R for the interest rate. And we just multiply those two quantities together. If R is an annual rate, then at the end of 1 year, the interest would just be your principal times your rate. So let's say there's a $100 and the rate is 2%, right? Well, 100 times 2% is $2. The interest would be $2 at the end of the year. Okay, so if you invested $100 at 2% simple interest, annual interest rate, you would have, after 1 year, you would have earned $2 in your account, and you would now have $102. Okay. Now, a lot of times interest is calculated by compounding. So what's that mean? Compound interest is computed on the original amount borrowed or invested plus any accumulated interest. Okay, so let's see how this works. So if R is an annual rate, then what's our accumulated value? So the accumulated value, A, is what the balance is. What's the amount that you've invested, or what's the amount that you owe? And so the accumulated value would be what? You got the principal. Let's look at it from investing. So let's suppose you put in a principal, some amount of money, P, and at the end of 1 year, how much are you going to have in your account, A, your account balance? Well, you're going to have, of course, the amount you invested, P, plus the interest. Remember, the interest was what? P times R, right? So here's the amount you invested plus your interest. So this would be like the $100. And then if it was R was 2%, 100 times 2% would be $2. $102 is what you'd get total, right? So there's the two parts. Algebraically, notice I've got this common factor of P, principal I can factor out. Okay, so we're just going to play around, manipulate this to get a formula is what we're going to do. At the end of 2 years, what would the amount be? So assuming we're compounding every year, then what's going to happen is they're going to now look at your amount at the beginning of the second year is this amount, right? Right. So that's how much you have in the account, P times 1 plus R. Okay, plus the interest. Well, the interest is going to be that P times 1 plus R times what? The interest rate, right? So we're going to take the amount that you have at the beginning of the second year, and at the end we're going to add in this interest. Well, there's a P and a 1 plus R factor that I can pull out, and what am I left with? 1 plus R. Right, so I can factor out this P from both and this 1 plus R from both, and I'm left with what? Here I'm left with 1, here I'm left with R. So it's P 1 plus R times 1 plus R, which is P times 1 plus R squared. Okay. Well, we're going to see what happens at the end of 3 years. You take this new amount, right? That's your account balance, the amount in the account, plus the interest, which is the amount at the beginning of that third year, times the interest rate. Again, I'm going to factor out P and a 1 plus R squared, leaving a 1 plus R, and I get P times 1 plus R cubed. So you see a pattern here, I think. Notice at the end of n years, this will be the accumulated value in the account. Okay. Now, most saving institutions have plans that compute interest more than just once per year. For instance, it might have monthly compoundings, for instance. Now, the number of compoundings per year, we're going to use the letter N to represent that. So we've got a lot of letters here. We've got A and P and R. I also had an N up here, so I'm going to have to change that to something else. We're going to use T for years, as we'll see here in a minute. But N is now going to be the number of compoundings per year. So here's some common compounding periods. If we compound semi-annual or biannual, there's 2 compoundings per year. The length of the compounding period is 6 months. Quarterly compounding, N is 4, right? 4 times per year, every 3 months. Monthly compounding, N is 12, 1 month length, and so on. So we can have different compounding periods. All right. So with that, here is the formula actually, and so I'm not really deriving this. We didn't quite get there here. We have to do some manipulating here. Basically, we'll explain here in a minute. So this is the account balance if you invest a principal of P after T years at an annual rate of R, and N being the number of compoundings per year, and T is now the number of years. Okay, so this works from this because the interest rate now is effectively what? The annual interest rate divided by the number of compounding. So this will be the interest rate per compounding period. And N times T will be what? Number of years times compoundings per year, total number of compoundings. So this comes directly really from this formula here. But this is our compound interest formula. Okay. So let's see if we can use this to answer some questions. That formula up there at the top. So if you invest $100,000, you probably got that just laying around right in your pocket, $100,000 right now to invest. Yeah, right. Okay. So if you have $100,000 and you invested at 8% compounded annually, so this is going to be an annual rate, 8%, compounded annually and equal 1, what will the account balance be after 10 years? Okay, so what is our values here? The principal P is the 100,000. Right? The interest rate R is 8%. Now what is 8%? Is that 8? No, 8% is 800ths. 0.08. It's real important that you understand that 8% is not 8, but it's 0.08. It's 800ths. So if you get that wrong, you're going to have an incorrect calculation. If you put R as 8, that's 800%. And if you can get 800% on a return, please let me know. We'll make lots of money. Okay. N is 1, we know. And after how many years? T is the number of years, 10 years. Okay. So what's our account balance? A is what? The principal P times 1 plus R, which is 0.08 divided by N. Well, N is just 1, so that's just going to be 0.08 to the 10th power. So this, of course, in here we can just write as 1.08. Okay. So now 1.08 to the 10th power, we're going to need some technology to help us with that, right? So let's see what we get. Let's just do the whole expression. 100,000 times 1.08 raised to the 10th power. Okay, so at the end of 10 years, to the nearest penny, let's round that off to the nearest penny, is $215,000, $215,892 and that 4.9 will round off to what? So the second, that 9 there rounds that up to 50 cents. Okay. So in 10 years you'll have that much. Of course, you got to start with 100,000. So what was the interest? What was the interest, right? If we subtract the 100,000 principal, right, the interest is $115,892.50. That's the interest that you earned on that. Okay. Now, let's take it one step further. What if you invest $100,000 at 8% compounded quarterly? What will the account balance be after 10 years? So everything's the same here except what? The n equal 4 part, right? So now my account balance is 1 plus, and remember the formula, it's r divided by n to the n times t power. So r is 0.08 divided by n, which is 4, to the n times t. 4 times t is 10 power. And I can actually simplify this, I guess I will in this case, 100,000, because this 4 divided by 0.08 divided by 4 is 0.02. So this in here is 1.02. 4 times 10 is 40. So 100,000 times Alright, so now we get 220,803.97. So notice we get a little bit more money, right? The interest is increased, and that's because of the compounding. So increasing the compoundings periods, the number of compounding periods in a year is going to increase the interest, because you're gaining interest on interest. That's why it's called compound interest. You're earning interest on interest. And so your money, we say, grows faster in that sense. Okay, well, this is fun. We made more money. Let's see if we can make more money. Let's compound more. Let's compound 12 times per year, or monthly. Okay. So the only thing different now is everything else the same, just n equals 12 now. R is still 0.08, n is 12. So that's r over n, remember? And then it's what? To the n times t power. N is 12, t is 10. Okay, so I'm not going to simplify anything here. What I'm going to do is just in the calculator now, I'm going to do 100,000 times 1 plus, I'm just going to do 0.08 divided by 12. And I'm going to raise it to, I can do 12 times 10. This time is 120, right? And there we are. So you definitely want to make sure you practice with your particular calculator that you can do these calculations. You will need a calculator to do these calculations. Okay. Now, notice, we got more money, but it wasn't quite as big as a jump. We went from one compounding, 1 per year to 4 times per year, and we gained almost $5,000, right? And now going from 4 to 12, we gained, but only about $1,000, right? So we're still gaining money, but it seems to be slowing up a little bit. Let's get more money. Let's compound daily. Okay. Now I'm going to use n as 365. Sometimes people use, bankers will use 360. There's 365.25 days in a year about, but we'll just do 365. Okay. Let's just do that. So here we've got same amount invested, same interest rate, 0.08. Now n is what? 365 to the n times t. 365 times t is 10. All right, let's see what kind of money we get now. We're doing a bunch of compoundings every day. So here's the 100,000 times 1 plus 0.08 divided by 365 raised to the so 3650, right? 10 times 365 is 3,650. .59, right? Okay, so looking at that, you know, we did gain again, but this time only about, not a big increase, only about $500 increase here. Right, a little more than $500 increase. So, you know, big jump in number of compoundings, but you know, it's not like a big increase in the amount. It's still increasing, but not a bunch. And that's true. What's happening is we're getting closer to something. What if I were to compound every hour? Can I compound every hour? Yeah. How many hours in a year? Well, there's 365 days in a year and 24 hours in a day. So if I just multiply 365 by 24, that's the number of compoundings we're talking about. So let me do that in the calculator. All I'm going to do, is I'm going to, instead of dividing by 365, I'm going to put that in parentheses, 365 in times 24. Okay, so notice in my denominator now, 365 times 24, that's the number of hours in a year. That's what I'm dividing by. That's R divided by N. Now I've got N times T, and so this is the number of times we compound if it's daily. So if I just multiply, I need to put this in parentheses though, first of all, because I need the exponent to be calculated before I do the exponent, times 24. So now this will be the number of total number of compoundings. Okay, and I have to put that in parentheses so that I get that exponent before I do the exponentiation there. All right, so compare that to our answer here. Now, look at the increase. We go from this to this. It's only an increase of less than $20. We're still increasing, but less than $20. So, big increase in terms of number of compoundings, but not a big increase. So this process is kind of slowing up. Seems like we're getting closer and closer to something as n gets bigger and bigger. This account balance for the same principal, same interest rate, same number of years. This process is increasing, but it's kind of approaching a fixed value, if you will. It's like we have a horizontal asymptote, and indeed we do. In fact, what's the best we can do? Okay. Well, the best we can do is to take n and just let it get bigger and bigger and bigger. We say let it go to infinity. Or what we say, continuously compound. So continuously compound interest is what's the limit of this process as n gets bigger and bigger and bigger. And it turns out that changes our formula. The continuously compound interest formula is calculated by this formula, A of t equals P. Hey, there's that natural base we introduced last time, e to the RT. And if you remember the way we introduced e, it was a process where we were taking n and n in this expression. We were taking n as n goes to infinity. This expression was going to approach e, we said, right? And so you kind of get a feeling, because this kind of looks like that compound interest formula in a way. We can manipulate it and get it to look like that. And we can show that indeed as n goes to infinity, where n is the number of compoundings, we get this formula. Some people like to call this the Pert formula, P-E to the RT, but it's principal times e raised to the RT power. So again, A is the count balance after t years, P is the principal, R is the interest rate. There's no compoundings here, right, because we've pushed n to infinity. So we say continuously compound is the way we do that. So what's the best we can do investing $100,000 at 8% compounded continuously? What will the account balance be after 10 years? Well, P is what? 100,000. E to the R, which is 0.08, times T, which is 10. Right? Same values as we had before. So this is 100,000. 0.08 times 10 is just 0.8. Okay, so that's the best we can do. Well, how much is that? So 100. Oh, by the way, I don't think I've showed you this last time, but some of you probably already know. There is a key in the calculator for the number E. There's actually two locations. Let's do this one. Second E. All right, so here's the value. As we said, this is the value for E, somewhere between 2 and 3, 2.71828, about. There's also a key in the calculator where you can do powers of E. I'm going to use that one in this case. So I've got 100,000 times, and then I'm going to hit this key here, right above, right next to the 4 key, so it's second. I want to get the yellow E to the X. And what it does in the TI-83, this old school one, it does like this. If you have a more newer calculator, it might put it up as an exponent. And the exponent's what? 0.8. So what do we get there? 222,554.09. And that's sort of the best we can do. Remember, this was what we could do if we did it every hour, compounding every hour. So not a big jump from every hour to continuously compounded interest, right? Only, less than $1 increase. Okay, but this is the best we can do. The best we can do. Now, so this is, you'll need to practice this. There's lots of variations. We can compare different compoundings, different interest rates, and see which investment might be better. And so continuously compounded interest and compound interest formulas are going to be important, and to be able to evaluate those in using your calculator. Now, look at one last example. There's other modeling problems where exponential functions come into play, and here's just one example. This is a model that someone created to model the percentage of college graduates among people ages 25 or older, X years after 1950. This model here can approximate that percentage. So what percent of people ages 25 or older were college graduates in 1950? Okay, so X is the number of years after 1950. So in 1950, what is the value of X? X is 0. Right? And so what we're looking for, what percent of people, that's G of 0. I want to figure out the output to this function when X is 0. So that would be what it is in 1950. Well, if I look at this, I get 38.8 over 1 plus 6.3. E, now if I plug in 0 for X, what happens? This is negative 0.051 times X, but X is 0. 0 times anything is 0. I just get E to the 0 power. What is e to the 0 power equal to? E to the 0 power is 1, not 0. Remember, e to the 0 power is 1. So this equals 38.8 divided by 1 plus what? 6.3 times 1 is 6.3. 1 plus 6.3 is 7.3. Okay. And so if I do that division, that's about 5.32. We rounded off to 2 decimal places. So what percent of people ages 25 or older were college graduates in 1950 rather? Answer is 5.32%. Well, what percent of people aged 25 or older were college graduates in 2000, assuming this model remains accurate? All right. Well, in 2000, what's the value of x? X is the number of years after 1950, so 2000 is 50 years after 1950. So what are we looking for? We're looking for g of 50. So that's 38.8 up top, looking at this formula. 1 plus 6.3 e. This time I'm not going to be able to put 0, right? It's going to be e to the negative 0.051, negative 0.051 times what? 50. Right? X goes right there. So that x goes right there as an input to this function, right? So just replace x with that value. So I've got to figure out this exponent and proceed. I'm going to do this all at one time in the calculator. So I'll show you how to do that here. So I've got 38.8 up top, and then I'm going to put everything in the parentheses down below, right? I need to make sure I do that. 1 plus 6.3 times, and then I'm going to use this, key right here, right, e to the x key. Okay, and it gives me in this version gives me the exponent, right? And then in parentheses, what do I need to put? Negative 0.051 times 50. Okay, close parentheses on the exponent. So make sure that whole exponent has to be in parentheses, because you got to do this multiplication, right? The negative 0.51 times 50 in parentheses first, and then you're going to raise e to that power. And I also need to close parentheses on my denominator, so I need another parentheses there, right? So closing the parentheses on the denominator. So there it is, and my estimate is, rounded off to 2 decimal places, about 26.01. And so it's right at 26%. 26.01%, but right at 26%. Okay, so again, getting used to this new type of function, exponential function, getting used to this new number e, the natural base, which is about 2.71828, and getting used to compound and continuously compounded interest. That's the type of thing now you want to look at in the homework.